question?
Sorry, I
Oh,
started too late, but really
that's fine.
question.
So the general question is, why is machine learning exploding, and why now, right? Um, so I guess then this can be explained from three perspectives. And what I have over here in the middle is the algorithm level. As you can see, theorism behind the machine learning, and particularly deep neural network, has made leaps and bounces in recent years. People know how machine learning works partially, although not completely. But no matter how people are able to deploy those solutions into many applications, at the edge devices or to the cloud. Well, my background, in fact, were on hardware designs. And so we know transistor scaling enable large chipset and the massive parallel executions. And of course, some people here are working on emerging architectures and that also provide a promise and for huge gains in energy efficiency. So in other words, we're able to integrate more devices on the chip or the systems. Um, Also on the application domains, people talking about the importance of big data. Well, with an prevailing deployment of an edge devices and cloud devices in different size and different functionalities. In fact, right now we are able to collect different data and use them wisely to many problems altogether. So the three factors and work together and entangle together. Um, my personal feeling again is, in the development of the hardware is extremely important among the three major factors. In today's talk, we'll focus on the hardware development. Talking about the accelerator designs on conventional platforms, industry as well academia have put a lot of efforts. I roughly listed, some company examples and active in these domains. But more importantly, I wanted to bring up your attention on the mismatch between algorithm level and hardware level. So the table here summarizes a few perspectives on this. For example, if we're talking about the reconfigurabilities, usually at algorithm level, it's maybe just a few lines in code. And when we're talking about the hardwares, and depends on what kind of the fabric, some of them are easier and some of them are pretty difficult. So how can we combine algorithm and hardware co-design since to maximize the efficiency? And how can we combine them to offer the best performance? This has been tracing for many years. On the other hand, many companies has been working on new architecture and system designs. Again, here I give very famous examples in past years also. For example, Google Tensor Processing Unit, TPU. It is a custom ASIC design for machine learning for DNN. It provides a lot of 10 times better optimized performance and provide efficiencies and for machine learning particularly. ARM-based SpineAche project is also very important. It was initialized multiple years ago, and it's part of the European Human Brain projects. As you can see, the approach integrated many ARM embedded processors and with the DDR SDRAM together for neuromorphic tasks. Well, in recent years, I guess, and IBM TrueNorth and the Loihes are more popular and famous. Both designs and tend to integrate a lot of neural synaptic cores, offer a huge amount of neurons and synapse. While the operation goal is to enable the cognitive operations while under very, very low power consumption. Okay. Um, so these are the approach in the conventional domains. And my research, in fact, majorly focusing on the analog computings and in memories. So in today's talk, I will start with my research about RAM, resistive memory-based neuromorphic chip design, and then moves to the cross-layer co-design and co-optimization, particularly focusing on efficiency and reliability. And at the end, I will give a quick conclusion about the talk and introduce my group as well. All right, so let's start with RM-based and neuromorphic chip design. And in this sessions, and I will primarily focus on a little bit device, but more circuit level exploration. So here I mentioned about the resistive memory or resistive random access memory, RAM. I actually at the beginning back to 2009, we took it as an example of memory stir devices. So structure-wise, it's a pretty simple. Let me have a laser. Yeah, the structure-wise, it's a pretty simple. It's like a two terminal devices. We can apply voltage or current across the device to change the resistance level. And of course, and if the external excitation is very small, we are able to detect the resistance level of the device as well. So we call this is a programmable resistor with analog states. This is a single device. We can also looking at the array levels. Usually we call this as a memory stir crossbar array. As you know, this picture illustrated, we kind of have a top mantle across and bottom mantle along orthogonal directions. At every cross point, and there will be a memory stir device. But more importantly, if we're looking at this in structures and the array structures, and when we apply analog voltage and from left along the horizontal directions, and then collecting the current at the bottom neurons, the current across in each bit lines and can be taken as an weighted, the summation of the weighted input voltage. And that the weighting is determined by the conductance of those crossbar devices. Okay, so in other words, it's naturally realize the matrix vector computation, and we take it as an analog computing format. So the structure shows in high density. It also shows an analog to the synaptic network, and therefore many years ago, more than 10 years ago, it's gained a lot of attention from industry and academia, and say how can we apply this to matrix operation and maybe some neuromorphic computing fabric. My own research actually start with RMs for computation and using bring state in a box algorithms as an example. It is an associate memory examples, and what I mean over here, for example, here is a recall functionality. XT represent the input vector. So the input vectors will work with the matrix. And then apply with the squash function, basically constraint is an maximum and maximum and minimum values, and generate the output vector xt plus 1. So if the old vector and the new vector does the same, and then we say the computation converges and we can stop over here. If they are not the same, then we supply the new vector as an input and feed it into the computation with the matrix again. So it takes an iterative and loops until the entire process is converges. So we take this approach as an associate memory, and the reason we choose it at the time was it has a better performance and easier controllability. So in our designs, and again, many years ago, like 10 years ago, we propose to start with initial input vector and applies to the memory-star arrays. And then at the bottoms, we collect the current and do the computation. So over here, the initial version, we use in 2 memory-star arrays because physical devices can only represent a positive weight, while the original algorithms could have a positive and a negative values. So we subtract the output from 2 arrays to mimic the functions and of the original BSB algorithm. And of course, in the following part, follow the philosophies, and we basically compare the output with the inputs and detect whether converges of the computation. If not, and then we will send the new computed outputs and use it as the new input. This is the general structures, and it was pretty successful. And later on, then we start deploy them on hardware designs. So the previous version, actually, we start with analog voltage as an input. So the entire computation, as long as the data representation are in analog. But later on, so when we really deploy on the hardwares, we find that at least at interface, the analog format caused a lot of complexities. And then we change to the spike-based and neuromorphic designs. So the philosophy are still very similar. The only difference is in these versions, the input is represented by series and spikes. And of course, the higher frequency of the spikes indicating the higher amplitude of the signal. So while we're doing this, and what we expect at the beginning is the output generated by the integrate and fire circuits, its spike frequency shall follow in linear relation. However, our simulation and testing didn't give us such a nice results. What we find is along with the increase of the summation of the weighted inputs, the pass number increases as expected, but eventually getting kind of saturated. So the reason of this is in real designs, and when we have an IFC circuits, it has a maximum operation speed, charging and discharging. So once it's reaching its an operation speed, the spike generation cannot be improved anymore. That's why we have this saturated situation. Another observation, in fact, as you can see in this and zoom in small figures, and for the same input amplitude, the spike generations and could have small variations. Well, the reason here is when we looking at x-axis, it was calculated based on the ideal situations with the input and also the conductance. Well, in physical implementations, and we have to consider, for example, the parasitic capacitance and resistance along the bit lines and the word lines, and also the variation of the signals. So it shows in some shifting over here. In other words, in real designs, we have to consider a lot of more. Back to 2019 also, we finally be able to process and fabricate the processing engine design with the in-situ neural activation we call ISNA, integrate 64 kilobits RAM on chip. Okay, here is the general architecture as I showed over here. The bottom part is similar as an RM design, and the top part were the add-ons of neural activation functionalities. Okay, so in our kind of a neuron design or output circuitry designs, and we actually using capacitors. Yeah, we're actually using capacitors and to general spikes. And in order to make it happen and reliable, we adopt the op-amp from a positive feedback to the accelerator, and use the response of the CS to control the signal qualities. In this designs, and we also use current measure to scaling down the bitline current, because in real neural network applications, and the result current along the bit lines and can have a very large range. It could be several microamperes and to several million amperes. And especially back to a few years ago, the device reliability, the device that we could access was not very reliable. So we prepare for large range during the designs. Okay. So in this designs and CA, the current amplifier first to drive bit line and source line, drive the bit line, and the source line sync current by connecting to the ground, and then the op amp stabilize the rate voltage. At the last, we actually apply additional phase compensation. This is because in our designs, we have two positive feedbacks. One is the op amp feedback, and another is an IFC positive feedback. So we have to adjust the pole of the entire circuits to ensure it's function properly. On the right-hand side are the simulation results. And first of all, the top figure shows our current amplifier designs can send input current range from very small up to kind of a 1 milliamp. This is the blue curve over here. Okay, and if you're looking at the bitline voltages, and it's stables and approximately. The bottom figures and actually shows that with appropriate phase compensations, the responses and can quickly converge the stable stage. In this designs, and we have two knobs, and during the debugging and the testing, the reference voltage here, as input of the current amplifier, is the read voltage of B lines. And so basically, when the reference voltage increases, indicating big current also increases, and so we can use this to tune that. And also another knob is the threshold voltage. This controls the threshold of capacitors and charging and discharging. So when we lower the threshold voltage, the charging and discharging could be easier. So with the two knobs, and actually we measure and test the spike frequencies, and those curve as trend wise, as you can see, it's very alike as the previous curves I showed, right? But with the different combination of the reference voltage and threshold voltage, we kind of can slightly tune the shape of neuron designs. And the purpose over here is to make it like tangent or clip the ReLU functionalities. The following are quite easier to explain. Essentially, during the testings, and we try to trade off between the precisions and the performance, and then we test the different configurations and say what is the peak performance and average power and the power efficiencies for our design. So here's the diphoto of our designs. We also measure the true performance for the real networks like multi-level perception, and also small CNN networks on MNIST and the ciphers. I don't go to a lot of details over here, but several interesting observations we have is, for example, for each group of in the bar here, the left dark one is the ideal, like algorithm level, and the red one is an algorithm level, but applying binarized neural network. So, and then the blue one is when we program those in binary ways to the systems, and still test that at algorithm with the softwares, and the last one were the real measured results. So what we find is, in fact, for the CNNs, it performs pretty well. For the multi-levels, and there's a performance job. This is mainly because of the simpler network structure, and also the use of the convolutional layers, and kind of can compensate the performance loss as well. So this is in our work like about 2 years ago. In recent years, and our group moves to the um, move from the spiking like rate codings into temporal codings. Essentially, what I mean over here is, and we tend to encode data to spike times, and so more using the temporal informations to represent the data. Okay, so we first present the time to first spike scheme. Basically, it encodes the data to the arrival time of a single spike in a given time window. So, all the data will be represented by one single spike, and therefore it offers a high efficiency. Um, so in this schemes, and there are a lot of interesting questions and to answer. For example, how can we map the excitatory and inhibitory synapse to the crossbar array, and how to leverage the event-driven property of the spiking neural networks and to maximize the energy efficiency. Very quickly go over this, and this is in our design schemes. And so in this design, and we also use in two columns to represent the excitatory and inhibitory weights and putting them together. So each paired over here, as you can see, the two bit lines are connected to two real post-neural modules. Okay, so the module obviously is more complicated than the previous versions, but if you're looking at each column, so it will be very similar to the previous version. The trick over here is, and in this designs, we apply the threshold voltage to the inhibitory, neuron designs, and that we have a positive and minus, negative and minus, and the threshold. That's the major tricks we had. Okay. Beyond this, and we also apply some techniques and to improve the efficiency and the robustness of the design. First of all, as our circuit shows that the current amplifier dominant the power consumptions, and so we tend to only turn on the current amplifiers when necessary. Okay. There are also some other schemes in, for example, timing threshold adjustments. What we find is we use in timing to represent the strength of the signals. And so earlier spikes and represents a stronger activation, while the later ones and contribute less to the overall accumulation of the next layers. And so we observe which threshold is making more sense and trying to minimize the spike generations. So this is we call it early stop, but analogs to the machine learning designs, and this is kind of a dynamic activations. I mean, on this page are more like the results, and considering the time, I will bypass this page. But if you have any questions, then feel free to email me. The second part of my talk today is related to the cross-layer co-design, and our aim is to improve the efficiency and the reliability. Many of you perhaps are already working on the DNN models, and you may already observe like sparsifications and prunings becomes very important. In fact, this figure was very popular in recent years. It's essentially indicating the performance of the neural network measured by top one accuracy, kind of related to its an operation requirement. It becomes more obviously if you kind of taking one series in networks like ResNet, 18, 34, 50, 101, and so on so forth. So the larger networks and offers better accuracy. The larger networks requires more operations, and the size of the circular grows up, indicating a bigger network as well. So bigger networks offer better accuracy, but requires high support at hardware levels. And so people tend to sparse and prune those techniques and trying to reduce the size and reduce the hardware cost. So talking about the specifications, and we could apply weight sparsities, activation sparsities. We could also goes into this like bit level sparsities and inherent sparsities. I'm going to briefly talk about the weight sparsity and bit level sparsity today. So years ago, our labs proposed a structure sparsity. So what we find at the time is an common sparsity techniques and algorithm didn't consider the hardware implementation requirement. So the approach was reduce the number of non-zero weight parameters only. So I given two examples to illustrate. For example, non-structured sparsities and all the dots are non-zero elements. So in this example, 94% of the elements are zeros and can be removed. And in our structured sparsities, we tend to remove the weight parameters and by columns or rows. And as you can see, we can only remove 91% of the elements. However, when we apply those structures to CPU and GPU, a lot of the hardware platforms and the structured approach can really gain performance, can really speed up the performance, while the top one were not able to. Okay, so this is basically because in non-structured weight distributions and didn't consider the memory access patterns, and so a lot of times, when you apply to the hardwares, and there's not much we can do. So we still maintain the structures. So at algorithm levels, and we propose what we call the structured sparsities, and the basic concept is the user need to group the weights. So when you group it, it could be like entire filter, it could be a channel, it could be some shape along convolutional layers, and could be the entire layer as well. So you just group those in weight parameters, and then next steps apply the group lasso regularizations along groups. For example, in this one, assuming you have a 5 weight elements, and then we split it into 2 groups with the 3 and the 2 elements and separately. And then we apply group lasso on each group. So this is for the first group, and this is the second group. And the next steps, then we sum group lasso over all the groups, and you include it into the regularization term. Okay. And then, the regularization term will be applied to the optimization objective during the training procedures. The remainings, and we can let the training procedure run, and they will automatically trying to improve certain groups from the definition. So the methodology itself, actually, we achieve quite significant success. The middle figure here shows our results compares to the non-structure in orange and our method in green. So simply speaking, the curve shows the sparsification levels. We are not as good as the non-structure ones. But on the other hand, if you compare those in bars as in true speed up, our case always kind of a benefit. So the method have been adopted by like Intel, by Microsoft, and also some companies. So we not only apply this to CNNs, but also LSTM in recent years, and actually we also applies to transformer and other model structures. So I mean, talking about the specifications, and if you goes to real algorithm levels, and people also talking about the difference of an L1 regularizer versus an L0 regularizer. And the figure on the right shows the contour and the gradient direction of those two regularizers. So for L1 regularizer, it is differentiable and convex. so it is easier to optimize. However, the value of the L1 regularizer is proportional to the scale of the parameters, so it can only scale down all the parameters with the same speed. This is indicated by those arrows, okay? So in other words, for large elements, um, it might apply penalty as well. So generally speaking, this is not desired in the design. Well, if you compare with an L0 regularizer, it's directly reflect the sparsity by definition. So it's a scale invariant. However, L0 regularizer provide no useful gradients. The gradients is either infinite or zero. So infinite on x-axis or zeros, anywhere else. And so it cannot work directly with the gradient descent. We need actual helps on this. So we extended work and proposed to move beyond L1 and L0. And what we proposed is we call the Hauer square. The Hauer square is an kind of a square version of the Hauer regularizer. It's differentiable, it's a scale invariant, and it has the same range and a similar minima structure as L0. Um, so, a lot of a concept over here is very alike to our previous in structure sparsities, and because then we can also apply this to the structure pruning. I just wanted to quickly show why this is particularly useful. So for example, if we observe the gradient of the Hauer square regularizer with respect to the each elements in the weight matrix. So the big difference is this in subtraction term. It induces what we call the auto trimming effect. What does that mean? So bottom figure over here shows the gradient descent path and during the optimization. So x-axis is the training epochs. And each curve representing kind of a random selected the weight parameters and how it's evolving during the training procedure. Okay, so the dark dash curve, in fact, corresponding to the relations and of these two terms and representing the auto trimming threshold. So as you can see, any weights start with the below this trimming threshold, it goes to decrease and then reach to zero. Well, for large weight, however, it can contain its large amplitude without being affecting much. And of course, the trimming threshold gradually increases. And so, when we train for a long time, it's kind of getting more parameters and removed. Okay, so in other words, it's maintains a large weights and prune out the smaller weights. On this page, and I show the results and very quickly for elements-wise sparsity, the proposed Hauer square further improved the model compression rate. And if we looking at the structure sparsities and we actually tested on group Hauer regularizer on compression ResNet for cipher. And here is the contours and flops and top 5 accuracy. And as you can see, the Hauer kind of performs better than previous and SOTAs. I mentioned, when we doing the machine learnings and the neuromorphic computings, and we need to consider cross layers. And so one interesting case and we find is, and we could apply mixed precisions and with a bit level sparsity. So quickly speaking, each binary information here can be extended to the binary representation. So a lot of times, if we find certain values, the same bits along the vectors and are all zeros, we can remove this. And this is particularly useful for crossbar or memory-based designs. And basically, this means the whole columns and can be removed, right? So For the bit representation, and here we follow dynamic scaling quantization procedures and use elements with the largest absolute value in each layer as the scaling factor. And then we uniformly quantize all the elements to n bits and then represent quantized value in binary form. And then we consider scaling factor and S, and then each bit in WS as an independent trainable variables. And so this is the bit level group lassos and representations and overall training objectives. Again, we actually have the paper published online and code available, and but the result here is just to show that with this methodologies, we can achieve much higher precision, mixed precision levels and much higher compressions. And but more importantly, this can be applied to the memory-based operation. So my last touch actually related to the reliability improvement. So if you're working on especially emerging memory technologies, you may realize the headaches and for not very reliable devices, right? Um, in our groups and recently we analyzed the distribution of noise and their frequency and temperature settings. And then we include relevant conductance and change to the RM cell during the training. And during this setups, we find in many cases, the noise and the frequency and the temperature settings and could dramatically affect the performance of the entire network. Well, when we included into the training procedures, the new trained networks and has a better resiliency of those noises. So we find another interesting thing we find is if we apply those setups and observe in different matrices, the design trade-off and shows it's very difficult to find a global optimal design configurations because in different configurations will favor certain matrices, but not all. Okay, so challenging task here is to find and design configuration that lies in the Pareto front and with the minimal cost. We hope it satisfies the design specification while with the minimal cost. So in our recent work published on ICCAT 2021, we proposed an re-estimate training procedures. The challenge over here is not only the trainings, the challenge is and the number of the available configuration combinations is huge, right? So for each configurations, since we inject the noise, the training time grows and very fast. So we tend to apply multiple objective optimization OOD methods to help us and find the right configuration quickly. I don't go through the details of this approach, but you can refer our paper. So right-hand figure shows the results obtained from the MOMOs. And on each figures, the number near the data points refers to the optimization iteration index. Like for here, we run more than 100 times and those kind of the run numbers. And here we only shows the Pareto frontier examples. So with these methods, and we can avoid high latency or high energy design. And from the Pareto set, we can also say some high cell resolution settings or some high frequency settings are possible with the properly settings and in terms of the other configuration knobs. Okay, so so far I just quickly go through what we studied in this domain. There are many other works that we have been done, but I like to quickly summarize. Basically, the progress of an hardware development need to match up with the upscaling of DNN models need to satisfy the application requirements. What we have been done is not only at the device and the circuit, but trying to grown up to the architecture and algorithm level and putting them together. I didn't present much on our architectural work, but essentially those are all important components and need to be integrated. Again, I guess, and even people have been talking about co-designs for years. It's still very important. We haven't reached its peak yet. And talking about design perspective, like execution speed, energy efficiency, design flexibility are very, very important and could benefit through this and co-designs. At the last, I also wanted to quickly introduce the technology roadmap of our group. We call ourselves as in Duke Center of Evolutionary Intelligence. We have two domains and currently run in our labs. One is on the AI foundation and another is on the application domains. So along this throughout, as you can say, we have been working on memory-based design since starting from like more than 10 years ago, starting from device level to the crossbars, and then to the accelerator designs. And then we grow this into the architecture designs and co-designs. On the left-hand side are some scalability issues involved. For example, I talk about the compression sparsity. We also have a work on low rank approximations and model reductions and so on so forth. And so this is also a large group. In fact, another a branch we have is the neural architecture search. We envision in the futures and we don't have to design those models by ourselves, but rely on more on the computers. And the right hand are our works on the applications, and we put quite dedicating efforts on the distributed computing and particularly federal learning. We also deploy all this to different hardware levels, from chip design to systems like embedded systems or large cloud. Okay, so this is actually conclude my talk. Again, I'm very happy to be here today, and very happy to talk more and discuss more with our audience.
Excellent. Thank you very much, Helen. Let me stop the recording and we get to the discussions.